Hello everyone from Math 1340, Statistics. It's Professor Winson here again with a video on your KnewtonAlta homework for section 7.3 titled Using the Central Limit Theorem. Okay, so we went from 7.1 to 7.3 in your OpenStax book on statistics. That's because 7.2 covers the central limit theorem for sums, which we are not going to be covering. All right, so we've skipped from 7.1 to 7.3. All right. Now I'll tell you something right now about this. Again, this homework is supposed to be related to the OpenStax book. So when you look at the objectives, there are two objectives, and I showed you how to do this in the section 7.1 video. How you can, using the central limit theorem to find a mean given a probability, using the central limit theorem for means to find probabilities, right, with your calculator, the TI-84 that I'm using. I did show you how to do this in the last video, so hopefully these two will be familiar. These two objectives, however, do not mention the central limit theorem. In fact, the only reason these are in here is because of a historical note at the very end of section 7.3 in the OpenStax statistics book, and I'll show you. So you have, using the normal distribution to approximate the binomial. Remember the binomial distribution. I hope you do. That was for a discrete random variable where you either had successes or failures, right, in n independent trials. And then this second objective is doing this again, using the normal distribution to approximate the binomial with your calculator, which I'll show you both, of course. Like I said, here's the OpenStax for section 7.3. And you see it starts off talking about the central limit theorem and how to use it and use your calculator to figure out certain probabilities. Right, again, and again, you can ignore anytime they bring up the central limit theorem for sums. Right? We're only doing central limit theorem for means. But they got all this stuff here talking about the central limit theorem. And then they have this at the very end, a historical note on how to use the normal distribution to approximate binomial probabilities. And then they go through some examples here. All right. Now, like I said, that's the only reason that this topic is in this particular homework. Right? It really doesn't have mention of the central limit theorem. The only objectives that do are these two down here, which again I've shown you how to do these two in section 7.1, but I'll still do a refresher when we get to problems on those. Alright, so the first objective, using the normal distribution to approximate the binomial. Alright, so I'll go to more instruction here. View instruction. Alright, so they give you a refresher here of the binomial distribution. Right, remember, the binomial distribution is a distribution where there are only two possible outcomes, right? Successes or failures. And in any number of trials, there is the same probability of success. Right? So independent trials. And it can be used to solve problems such as, if a fair coin is flipped 100 times, what is the probability of getting 60 or more heads? Right? We've done stuff like that before. I believe back in chapter 4 material. And the probability of exactly x heads out of n flips was computed using this formula. And again, I showed you how to use the calculator to do this as well. This was that n choose x, right, ncx, times, the probability of success on one trial to the x power, the x number of successes. 1 minus p would be the probability of a failure on each trial, raised to the n minus x power, which is the number of failures. Right. Okay, so again, they refresh your memory on the binomial distribution. And then they get into some more historical stuff here. Abraham de Moivre, an 18th century statistician and consultant to gamblers, was often asked to make these lengthy computations. What would be the probability of getting 60 or more heads? Back in the 18th century, that would have taken quite a while to figure something like that out. He noted that when the number of events, right, the number of coin flips increased, the shape of the binomial distribution approached a very smooth curve, and actually a bell curve. So I guess this is how this ties into the central limit theorem. Remember, this number of trials here can be thought of as our sample size, and as the number of trials or the sample size increases, the distribution gets closer and closer to being normal. Right, so I guess that's how this ties into the concept of the central limit theorem. So here the figures below, right, show the binomial distributions for 2, 4, and 12 flips. So this is when flipping twice, get probability of getting 0 heads is a quarter, 1 head is a half, and both heads is a quarter. And then if you flipped it 4 times, 0 heads, 1 head, 2 head, 3 heads, 4 heads, and you see the very nice symmetrical. And then when there's 12 coin flips, see it's getting closer to like being a nice continuous curve. And de Moivre wanted to find a mathematical expression for this curve, so he would be able to solve problems like this, right, much more easily. And that's what he did. The curve he discovered, called the normal curve. So he used a nice smooth bell curve to give an approximation to these bars, right? The distribution of number of heads flipped in so many coin flips. Okay, so the next part of this is using this bell curve, and remember, area underneath the curve corresponds to probability. So I can use this bell curve and the area underneath it to approximate probabilities from a binomial distribution. All right, so they have an example here. So assume you have a fair coin and you wish to know the probability that you would get 8 heads out of 10 flips. Alright, the binomial distribution has, now remember these formulas from again chapter 4. Remember the mean value of the binomial was n times p, the number of trials, times the probability of success on each trial. So there's 10 flips, right? 10, and the probability of flipping a head on each of them is a half. So 10 times a half, your mean or expected value here is 5. And then the variance for a binomial distribution, remember that sigma squared was npq, right? Q was just 1 minus p. So multiplying those, you get 2.5. 10 times half times a half is 2.5. And then the standard deviation was the square root of this, right? The square root of the variance. And it's approximately 1.5811. Alright, so a total of 8 heads. And you see they're calculating the z-score here. 8 heads minus 5 heads, 8 minus the mean, divided by the standard deviation. This, 1.897 is the z-score for flipping 8 heads. 8 heads is 1.897 standard deviations above the mean. Alright, so the question is, what is the probability of getting a value exactly 1.897 standard deviations above the mean? And the answer is 0. Because remember, the probability of any one specific point in a normal distribution, remember for normal distributions or any continuous distribution, the probability of getting exactly a singular value was 0. You had to have a range of values, right? Some sort of interval of values. So that's the issue with the binomial distribution. Right? The binomial distribution, had a discrete probability distribution. Right? Finding the probability of any one value will give you 0 if you're talking about, using a continuous distribution to approximate a discrete distribution. So, we use the normal distribution to approximate the binomial because the normal distribution is a continuous distribution. The solution is to round off and consider any value from above and below the value that we want to find the probability of. So we will consider any value from 7.5 to 8.5 to represent an outcome of 8 heads. I'm going to shade this area below. So if I'm flipping these 10 coins, right, and I wanted the probability of getting exactly 8 heads, and you use this normal curve to approximate it, you're not going to use the area just under 8. That's 0. There is no width. So you're going to go to the halves, 7.5 to 8.5, in that area to get your approximation. Okay, and then they talk about, here they talk about using a table, but you could also, they also say you can use a calculator. Alright, so you can use a table, standard normal table, or use the calculator with that normal CDF. Alright, I'm going to also draw a picture of this myself. Alright. So remember we had here x, say x represents the number of heads flipped. Right, x is a random variable for number of heads. And it's binomial. Remember that symbolism, the B for binomial. And there were 10 trials. And then remember this was in the 10 trials, and then the probability of success on each trial, the probability of flipping a head on each trial was that 0.5, right? That was the P. And the mean, they've already discussed, the mean value of x was NP 10 times a half, so 5, and the standard deviation was the square root of NPQ, alright, 10 times 0.5 times 0.5 again, and that was about 1.5811. Now if I was drawing a picture of this, and I'll actually show you how to make we haven't really seen too much how to make a binomial distribution on your calculator. I'll show you how to do that after I'm done drawing this. Alright, so got a little, I'm going to make a histogram. Alright, make a histogram. So not exactly like they had on the KnewtonAlta. They were just using straight up segments. I'm going to use a histogram. So down here, x is the number of successes, right? The number of heads flipped in these 10 flips. Now, x could be 0, and I'm going to try to evenly space these. 1, 2, up to 10. And of course, this is a number line here, so I mean, there is 11 and stuff, and there's negative numbers, but you can't possibly flip a negative number of heads, or 11 or 12 heads, when there's only 10 coin flips. Now, for each of these probabilities, now I could go in. All right, I'm going to actually pull the calculator up now to find these probabilities. Let me show you a quick way to get the list of all these probabilities right now. So remember that binomial distribution? I want to find binomial probabilities. I go to second, distribution, and then down to A, which is the, this was the binom. There was binom PDF and binom CDF. I want to find the probability of getting, exactly 0 heads, exactly 1 head, exactly 2 heads. If you want to find the probability of getting exactly a certain number of heads, that was this binom PDF. All right, so how many trials? 10. What's the probability of success? 0.5. And then what I'm going to do here is I'm going to leave the x value blank. Normally I'd put in 0 or 1 or 2 or 3, but if you leave it blank, let me show you what happens. And if you have an older calculator, you're going to have to enter it like this. You'll see the binom PDF come up, and then you put in the number of trials, and then a comma right above the number 7, and then the 0.5, the probability of success on each trial. Now look at what happens when I leave that third value blank, that x value blank. It gives me an entire list. Right? And the first number here, the first number in this list after the little brace, 9.7 times 10 to the negative fourth. So this is like 0.0009. This is the probability of getting 0 successes. Right. So I'm going to start making bars here. Now the probability of getting 0 successes is 0.0009. So basically nothing. All right, so off to the side here, I'm going to have the probabilities. All right, probabilities. So this has a height of 0.0009. Right, very, very short bar. A very, very short bar. And notice what I'm doing here with the bars. I'm having it so that the value shows up in the middle of the bar. All right, so that's what they were talking about by going to the halves. So you see like this, so this value at the far right of the bar on the number line would be 0.5, right? That is very tiny, I apologize, but that's 0.5. This value on the left side of the bar then would be negative 0.5. Right? So from negative 0.5 to 0.5, I get the bar, the whole bar for, 0 successes. And then on the calculator, again, so that was that first number, and then if I scroll through, the next number that shows up, see, is 0.0097. This is the probability of 1 success. All right, flipping 1 head. So 0.0097. All right, so I'm going to start doing this. This is very, very tiny. I'm going to mark off some stuff here. So let's say this is 0.1, 0.2, 0.3, 0.4, 0.5. I don't think anything gets that high. I don't think any of the probabilities get that high. All right, so 0.009. 0.009, very small. Again, very small. So let's say it's here. Right? So just about, it's just about 10 times higher than this, which still isn't very high. Right? Still less than 1%. So I'm just making a short bar. And it's going to look a lot better when I put it up in the calculator, of course. All right, so I'm going to do the next one, and then I'm going to kind of skip ahead and show you the final result when I'm done. But keep scrolling. Hit the right scroll here. Then this next number with see they got a decimal place, 0.0439. This is the probability of getting 2 successes. All right, and so I'll make one more bar here. Now, this was at point, 0.009, almost 0.01. This is at 0.04, so it should be about 4 times higher. But, just a little higher. I don't know. I don't want it to go too high, but it's almost at 0.05, which is like 5%, half of 10%. So I'm a little bit under the half here. So again, this bar is from 1.5 to 2.5. Right, the bar for two successes, and then the bar for 3 successes goes from 2.5 to 3.5, and so on. All right, so I'm gonna draw this out, and I'll be right back when it's fully complete. Okay, so I've gone through and made this histogram for a binomial distribution with 10 successes, and the probability of success is a half. Notice the symmetry here. It looks perfectly symmetrical with the middle bar being the highest. Now if the probability of success was 0.6, the peak would be to the right. If the probability of success was 0.4, smaller would be to the left. But do you see how I've got this picture here, this histogram, starting at negative 0.5 and ending at 10.5, right, for the last bar for 10 successes, 9.5 to 10.5. And you see how I can approximate this? Right, we can approximate this, get something pretty close to this with a normal distribution. So so x here is approximately, I'll say, and I'll do like the approximately equal to a normal distribution with this mean and this standard deviation, a mean of 5 and a standard deviation of 1.5811. So that would be like this here. Right? So again, I'm just kind of connecting the tops here with a nice symmetrical bell shape, right, in purple. Right, so something like this. I don't know. It's not perfect. Right, this is a hand drawing, but this purple curve I just drew, see, it has a mean of 5. Right, it has a peak right over 5 here, and a standard deviation of about 1.6 almost. So this inflection point should be at 6.6, and then the inflection point over here should be at 3.4. Right. So the one inflection point should be above 6.6, the other inflection point above 3.4. Right. And then if I want to find probabilities for the binomial, I can approximate. I can get a pretty close guess, because notice the area under the curve doesn't get all the area of the bars. Sometimes, some of the bars are sticking out here, but the area under this curve will give me a nice approximation to the areas of these bars in the histogram. Right. And let me show you even a little better picture. Okay, let me show you a better picture. I'll show you how to make a binomial distribution, a histogram, on your calculator. All right. So I'm going to go to Stat, Edit, and then down List 1, put the numbers of successes. Now, there's 0 to 10 here, and you could actually make a list from 0 to 10 and store it here, but I'm just going to enter 0 to 10. There's only 11 values. It won't take that long. Right, so I'm going 0 to 10, right, the numbers of successes down this first list. Okay. Then down list 2, all the probabilities of those successes. Now I already have those. They're what's popped up here when I did the binom PDF, 10 trials, probability p.5. So I just need to take this previous set here of all the probabilities and store it. Just hit store and see it takes the previous answer and stores it, stow, in list 2. I'm going to go second 2 for list 2 and then hit enter, and it'll say okay, repeat the values. But now look what happens when I go back to that list. Go stat edit, and see now list 2 is populated by all the probabilities, the probability of no successes, 1 success, 2 success, etc. Alright, now I'm going to make a histogram. So remember how to make a histogram. You go second, stat plot, go to plot 1 here, or whatever plot you want. I'll turn it on. What type do I want? I want to make a bar graph, a histogram. And then what's the list of data? Then what's the variables? The random variable is the number of successes. That was down list 1. And the frequency list. Now usually everything just counts once, but here there actually are frequencies or probabilities. This is your probability list. List 2. Alright, and then I'm going to change the window before I graph. I'm going to change the window. Oh, it's got F2 now. Alright, let's get out of here. Alright, so I'm going to change the window. And I'm going to do it so that I see everything I'm looking at here. Alright. So from negative point, I'm going to do from negative, I'll do negative, I'll start at negative 0.5 for the x min, and go to positive 10.5 for the x max, right, the beginning and end of my bars in my drawing here. This x scale will just be, how far apart all the notches are, 1 unit, right? All these bars are 1 unit thick. That's what the x scale will give me, and I want them to be 1 unit thick so that they represent, one specific number, one number of successes. And then the y min, y max, that'll be for the vertical. You can have it start at 0, but I'm going to have it start at negative 0.5, just so I see the x-axis. And then the highest probability was at like 0.26, so I'm going to go up to 0.3. Oops, I changed the x scale. X scale I want to be 1. Sorry. The y min I want to be negative 0.5. Y max 0.3. And now I'll hit graph. And look at, alright, maybe I'll change the y min actually. Just y min is 0. There we go. Alright, so this is 0 to 0.3 on the vertical axis, negative 0.5 to 10.5, and you see how the bars at the end are basically nothing. Right, if I hit trace on this, see how the first bar is so low it's practically 0. And then you keep moving along, and then you see that probability of 5 successes. See from 4.5 to 5.5 here. The probability of 5 successes was about 0.246. And then you get all these, and it's again, let's get out of the trace. Just hit graph again, and look at how nice symmetrical that is. Looks pretty close to bell shaped. And now what I'm going to do is put in over this, like on my drawing, the normal curve with a mean of 5 and a standard deviation of 1.5811. Now, how do you do this? How do you graph a normal curve on your 83 or 84 calculator? So here's how you do that. You go y equals, and then y equals, and then I got plot 1 on. Plot 1 is blackened up here. That's our histogram. And then y equals, and then when it's flashing, I'm going to go to that distributions area, second, distributions, and then this is the only time that the normal PDF is useful. Right? When we want to find area under the curve, the normal curve, we use normal CDF. But if you want to actually graph a normal curve, this is where normal PDF comes into play. Alright, so for the x value, just enter the variable x. And then mean 5. Alright, we said mean 5. And standard deviation, Now I'm going to make it a little more accurate. I'm going to put in that square root of 2.5, right? 10 times a half times a half, and the square root of that. I'm going to put in the square root of 2.5. There. And then I hit graph. Well, let's enter. Now I've got the normal PDF in there. Now look what happens when I hit graph. Look at this curve coming in. See, it's like the purple curve on my drawing. See, the normal curve very closely approximates this binomial histogram. It's not exactly the same, right? See how there's some bars? See how the area of some of these bars goes over the curve? That's why it's called, an approximation. Right. Okay, so that was a long thing, right? Putting all that together. But now, right, now going back to their example. See, now if I want the probability of getting exactly 8 successes, right? If I want the probability of getting exactly 8 successes like they asked, well, on my drawing here, the probability of exactly 8 successes is the height or the area of this bar. Right, that's the probability that x equals 8. Well, if you want to use the normal curve, it means you're going from 7.5 to 8.5 and finding the area under that curve. Now you see how the area under that curve goes a little bit more than the bar. Like not a little bit more, but it's different than the bar itself. So this is approximately going to be the area under the curve, right? Area under normal curve from 7.5 to 8.5. From x equals 7.5 to x equals 8.5. All right, let me show you on the calculator, all right, how these are incredibly close. All right, so get out of the graphs here. So let's find that binomial. Let's find the binomial probability and see that the normal area under the normal curve is pretty close. So if I go back to the binomial PDF, all right, binom PDF, 10 coin flips. The probability of success on each coin flip is 0.5. And I want the probability of getting exactly 8 successes, so I put 8 in there. See how this is 0.04394, blah, blah, blah. Now, let's find the area under this normal curve with the mean of 5 and the standard deviation of 1.5811. So that was, remember, distributions. You want to find area under a normal curve. That was normal CDF. Okay, now what's the lower value in this region, the area I've shaded here? That was, again, if I want the probability of exactly 8 successes, I'm going from 7.5 to 8.5. So I enter 7.5 as my lower value, 8.5 as my upper value. The mean of this distribution was 5. And again, to be a little more accurate, the standard deviation, the square root of 2.5. Right, the 10 times a half times a half. And look at how very, very close these are. See, 0.0434, right? It's good for the first, 3 decimal places. They're good till the thousandths place. Very, very close. But then a little off after that. But you see how the normal curve, the area under a normal curve, can very closely approximate binomial probabilities. And that's the whole point of this first couple objectives in this homework. All right, so from here on out, I'm not going to draw as extensive a picture, and I'm not going to make graphs on the calculator. I'm just going to talk about what you need to enter to find certain probabilities. All right. So they have you read through this and blah blah blah. Okay, and they go through another example. Now they use a table as well. If you want to remember, if you want to use tables, you've seen me do this before. If you want to use tables to find these areas, these standard normal tables, you're going to have to convert all the values to z-scores. All right, so if I wanted to do that here, I'd have to change 7.5 to its z-score. All right, so subtract 5 and then divide by the standard deviation, 1.5811. And I would also then have to change 8.5 to its z-score. Then look at a table, find the area to the left of the right value, find the area to the left of the left value, and then subtract them. Right, so it'd take a while. And you can read their example here, how they're doing, the probability using tables. I'm not going to be doing that. Right? They say using a calculator, normal CDF. All right, so let's get to a problem here. Now it says you may use the table or a calculator. All right, let's just save some time, use a calculator. So you flip a fair coin 16 times. So that's the n, right? Value, number of trials, 16. This binomial distribution can be approximated with the normal distribution, normal with a mean of 8 and a standard deviation of 2. Right, where the mean is 8, standard deviation sigma is 2. Approximating the binomial distribution with a normal curve, what is the probability of flipping 9 or 10 heads in the 16 tosses? Alright, so if you're doing 9 or 10 heads, you want to get that 9 bar and that 10 bar. Now, remember, the 9 bar is going to go from 8.5 to 9.5. And the 10 bar goes from 9.5 to 10.5. So if you want both of these, and you're talking about area under the normal curve, what region, you're going from 8.5 to 10.5. You're going to use a lot of halves when using the normal curve to approximate a binomial. All right, so I'll pull up the calculator and just go to that normal CDF. Second distributions, normal CDF. And to get the 9 and the 10 bar involved, I'm going to go from 8.5 for the lower value to 10.5 for the upper value. And they said that this binomial distribution was approximated by a normal distribution with a mean of 8 and a standard deviation of just 2. So what is this area? It's now they're saying round. Now it looks like they're rounding to the nearest hundredth, right? They have choices down there, 1,000. Just pick the closest one. So it's point on the calculator. It says 0.2956. That's closest to 0.3. Right, of all these choices, the closest is 0.3. Right. So it's really that easy. Again, you're gonna be using halves, right? Going to half marks a lot. Now they use the table also. I'm not doing that. All right, so here's another question on the same type of problem. This time, though, they're just asking you to fill in the parameters of the normal distribution. Right? So a fair coin is flipped 100 times, so n is 100. So let x be the number of heads. Now, so the probability of a head is again a half. So p is again a half. What normal distribution best approximates x? So what would be the mean? Remember, that's n times p, 100 times 0.5. Well, that'd be 50. Right, so the mean of the normal distribution, mu, is 50. And what would be the standard deviation? Remember, it's n times p times 1 minus p, and then the square root of that. So npq, 100 times 0.5 times 0.5, well, that'd be 25. And then the square root of that is 5, so they end up being nice whole numbers here, 50 and 5, for the mean and standard deviation of the normal distribution that approximates the binomial really well. You can read through your answer explanations, see the formulas coming up, and all that. So now, using the previous answer, right, we know that the binomial distribution is approximated by this normal distribution with a mean of 50, standard deviation of 5. Using that fact, they wrote it again down here. So as in the previous problem, right, a fair coin is flipped 100 times. X represents the number of heads, and the distribution of X can be approximated with this normal. Using this approximation, find the probability of flipping 54, 55, or 56 heads. So if I were looking at, my picture of a binomial, if I was making a histogram for the binomial, I'd want to include the 54 bar, the 55 bar, and the 56 bar, which would go from 53.5 to 56.5. Alright, so when I come up with the calculator here, and again, you can change the z-scores and use the table, but pull up the calculator, and I'm going to go to that normal, or I'm using the normal curve to approximate the binomial probability. If I want the 54, 55, and 56 bar, that's going from 53.5, so 53.5 for my lower value, to 56.5 for the upper value. That will include all three of those bars. And we found earlier that this binomial is approximated by a normal distribution with a mean of 50, so mu is 50, and a standard deviation of 5. Right, so sigma is 5 there. And it's coming back 0.14516, so 0.1452 about. And round the final answer to 2 decimal places. So if I rounded this 0.1451, 0.145 to 2 decimal places, 0.15. So 0.15, about, the probability of flipping either 54, 55, or 56 heads would be about 15%. Let me submit that. And wonderful, right? It comes back good. Again, read through the answer. Now, again, they're using the tables or the normal CDF with the exact numbers I entered. Okay. All right, so then this problem is no different than the last one, so I'll leave it to you. All right. Again, the probability P here is 0.5, 50%. It's not about coin flips, but it's still pretty similar. So what would be the mean? What would be the standard deviation of the binomial? And that would be the mean and the standard deviation of the normal distribution that approximate it. So I'm going to leave that one to you, or something like this to you. I've done one like this already. All right, and then using that normal distribution, so they say they want you to find the probability here of 52, 53, or 54. So you'd go from 51.5 to 54.5 with your normal CDF and a mean of 48, standard deviation of 4.9. Round your final answer to 2 decimal places. So again, I've done something like this already. Please know that the answer is not always going to be 0.15. It just happened to be that 2 times in a row here. All right. Now, they've already told you, I don't get why this objective is any different, why they have to have it be separate. Because, this is the same thing using the normal distribution to approximate the binomial with a calculator. And you've already done this. Alright, so this one I'll read through, and you have to just, round your answer to 4 decimal places this time. So Dakota is a quality control manager for a manufacturing plant that produces batteries for tablet computers. So based on prior history, Dakota knows that 0.6% of all tablet computer batteries produced are defective. So he selects a random sample of 1,200 computers. And again, now this time the value of P is 0.6% or 0.006, right? P is 0.006. And the N is 1,200. So he selects a random sample of 1,200 tablet computer batteries from a recently produced lot and tests each battery to determine whether it is defective. What is the probability that Dakota finds 5 or fewer defective batteries? 5 or fewer. So that means I would want the 5 bar and the 4 bar and the 3 bar, the 2 bar, the 1 bar, the 0 bar. And technically you can just go to the left forever because we're doing 5 or fewer. Now the 5 bar would go from 4.5 to 5.5. So the upper value of this region going 5 or lower would be at 5.5, not 5. All right, and then there is no, because we're going fewer, just no lower value. So I'm just going to put in some big negative number for the lower value. Okay, so I'm going to pull up the calculator then. We're going to use our binomial distribution to approximate, or sorry, we're going to use the normal distribution to approximate the binomial. So I go to normal CDF. Now the lower value, again, there is no lower value. So I'm going to put in some big negative number, right? I'm going to say negative and then, 5 nines, 99,999. The upper value, remember I mentioned we're going 5 or fewer defects. So if I want that 5 bar included, I'm going up to 5.5. The mean, remember, is N times P, 12,000, or sorry, 1,200 times 0.6, or sorry, 0.006. All right. Remember the P here was 0.6%, so 0.006. So I'm just putting an N times P there. And then the standard deviation, the square root of N, 1,200, times P times 0.006 times Q would be 0.994. And close parentheses on that. All right. And we're getting 0.26256, but rounded to 4 decimal places would be 0.2626. So 0.2626. Let's see if that comes up with what they wanted. Great. All right. So again, same deal. You've done this already, right? It's just a different description, different values of N, different values of P, and you're going to enter different lower values and upper values on your normal CDF. But nothing really changed from the first objective. Okay. All right, so I'm going to skip over all the other problems in this objective because they're all pretty similar to that last one. So I leave it to you. Figure out what's N, what's P. So then what would be the mean and standard deviation of the binomial distribution, and that'll be the mean and standard deviation of the normal distribution we use to approximate it. And then you just have to figure out what's the lower value and upper value of the region we're talking about, the region that we want to find the area of. So I'm just going to cheat on this. Again, you can pause my video here and read over what they had there. Okay, so same objective, same kind of problem. So I've already done one like that. Just going to cheat through it. I know you can't cheat through it, I'm sorry. But just to make this video a little shorter. Alright, and then looks like one more just like that. Okay. Alright, so now these last two objectives are actually on using the central limit theorem for means to find a given probability. So if you recall, hopefully you recall, now I'll go to the more instruction again. They're going to refresh your memory as to what the central limit theorem for means was. Right. Remember if you had a population and you pulled samples of size n from that population and then looked at the means of those samples, what was the distribution of those means? Well, the larger the sample sizes, the closer to normal the distribution of the means got, right? If you want to refresh your memory, go back to section 7.1. Look at the central limit theorem for means that I discussed in that video. And remember that the mean of those means, the mean of the x bars, the mean of the sample means, was just the mean of the original population. So mu x bar was mu. And the standard deviation of those sample means was the standard deviation of the original population divided by the square root of the sample sizes. So hopefully that sounds familiar. And then this particular objective is, finding a mean given a probability. So you're given an area under the curve and you're finding a particular value, the value on the number line, and that involved that inverse norm. So again, that was brought up in section 7.1's video. I've done this before. So you can read through this example. I will do one problem from this objective and then cheat through the rest. And there's another objective where you're given values and you have to find area under the curve. All right, so here, a video game company sells an average of 132 games a month. All right, so that's like the mean of the population. All right, if you look at look at all the months. Look at all the stores in a month. The average store for this company sells 132 games with a standard deviation of 9 games. So there's mu, there's sigma, right, for the original population. The company is looking to reward stores that are selling in the top 7%. So it says here, use a calculator to find the number of video games must a store sell in order to be eligible for a reward if the company is only looking at 36 of their stores. So there's your n, right? The sample size. Okay. So it says down here, if needed, round the standard error of the mean, that sigma x bar, to 2 decimal places, and round x bar up to the nearest whole number. All right. So I'm going to go to a piece of paper here. All right. I'm going to go to a piece of paper and show you some pictures. I'll draw some pictures. All right. So let's get rid of the calculator for a second. All right. So say x. Right. X was the number of games sold. Number of games sold in a month. And we were told that the mean value, right, the average number of games sold in a month by this company was 132. We were also told that the standard deviation for the number of games sold in a month by this company was 9. All right, now from this population, a sample of size 36 is taken. Now this is definitely 30 or greater. Remember, when the sample sizes were 30 or greater, it didn't matter what the distribution of the original population was. The distribution of the means of those samples would be approximately normal. That was the central limit theorem, what that stated. So I take a sample of size 36, and then we look at the average, how many games on average did these 36 stores sell, right? 36 stores. And X bar, right? We're going to look at this new variable called X bar. And X bar represents the average number of games sold in a month by these 36 stores. By a group of 36 stores. Or I'll just say a group of 36, right? So X bar here represents the average number of games sold by any group of 36 stores this company selects. Now, by the central limit theorem, right, CLT, the distribution of X bar, right, these means, should be approximately normal with a mean of, called mu sub X bar and a standard deviation called, sigma sub X bar, where again, mu sub X bar is the mean of this distribution of the means, the mean of the sample means is the mean of the original population, so 132 games. And the standard deviation of the sample means, or something what they call standard error, is the standard deviation of the original population divided by the square root of the sample size that was taken, right, the 36 stores. So this is 9 divided by the square root of 36. Now that's just 9 divided by 6, which is 1.5. So I don't need to round that to 2 decimal places because they said it in the question, if needed. If this went beyond 2 decimal places, then I would round it to 2 decimal places. And I'll draw a little picture here. Here's X bar, and it's normally distributed. So here's some symmetrical bell-shaped curve, right, going to the left forever and right forever. Underneath the peak, that value should be at 132, and the standard deviation is 1.5, right? So these inflection points should be above values that are 1.5. Remember the inflection points are above values on the number line that are 1 standard deviation away from the mean. So this inflection point's at 133.5. This inflection point would be at 130.5, and so on. You could mark off where 2 standard deviations, 3 standard deviations are, etc. Now what we're asked to find is what average value, what X bar separates the top 7%. So the top 7, so that's an area, right? So let's say this area here, right, forever, this is the top 7%. We're asked to figure, now we just want to know, what is this value? What is this particular X bar? What value has 7% above it? Now if it has 7% above it, right, that means that there's 93% below it, right, to make a total of 100%. I'm going to be using that number 93, or 0.93. Right, so I go to the calculator, and again, if we're given an area like I am here, and we want a value on the number line, that's using that inverse norm. So let's clear all this. So remember, go to distributions, second, distributions here, and then the third one down, inverse norm. This is if I know an area and I want a value on the number line. Now remember, this area is the area to the left of the value I want. Okay, so don't use 7%. The area entered in the calculator needs to be the area to the left, so that's 93%. So I'm going to enter 0.93. Right, don't enter 93. It's 93%, 0.93. All right, and then what's the mean of this distribution? 132. What is the standard deviation of this distribution? We found that this was 1.5. Right, and then I enter all this. This pops up, and this value here, and they want us to round to the nearest whole number. This particular x bar with 7% above it is approximately 134. Right, because 134.21, that round to the nearest whole number, that's 134. All right, so back here. So they wanted us to enter, what's the standard deviation of this new distribution, right? The distribution of the means. That was 1.5 we saw, right? 9 divided by 6. No need to round it to 2 decimal places because it said if needed, but we don't need to. And then what is that x bar, right? What is that value with the 7% above it, right? So you would need to sell at least 134 games, right? 134 games or more to be in the top 7% of these stores. Right. Oh, what happened? Is it 135? Or maybe they want 1.50 for the 2 decimal places. Let's see if that does anything. Okay, what do they got? All right, maybe it's 135. Goodness. Ow. It did say round. Oh, it said round up. Okay. Read carefully, folks. It did say round up to the nearest whole number, so that 134.2 that I had should have bumped that up like it asked me to be in the 135. My apologies. I did not read that carefully enough. I just saw round to nearest whole number. Round up. Alright, so my bad. But I did everything correctly. Alright, so everything I just did is what you need to do for this kind of a problem. Alright, so this one here, alright, I'll just pull the calculator up and do it on this screen. So the height of seaweed of all plants in a body of water are normally distributed with a mean of 10 centimeters and a standard deviation of 2. So that's like your mu and sigma. So use a calculator to find which length separates the lowest 30% of the means of plant heights in a sampling distribution where the samples are size 15. Now this is not 30 or greater, but remember, it doesn't matter when the population is normally distributed. All right, when the original population is normally distributed, it doesn't matter what size samples you pull. The sample means will have a approximately normal distribution by that central limit theorem. All right, so n is 15, and we want to find what's the value of x bar, what mean separates the lowest 30% from the highest 70%. All right, so back to the calculator. All right, this is, again, I'm given an area, I'm given percentages, right? So I'm going back to that inverse norm. All right, so second distributions, inverse norm. And then the lowest, we want to find the value that separates the lowest 30% from the highest 70%. So the area to the left then is the lower 30%. So I'm putting 0.3 for the area to the left. The mean of the sample means would be the mean of the population, so 10 centimeters. The standard deviation of the sample means would be the standard deviation of the population, 2, divided by the square root of the sample size, so the square root of 15. All right, these had sample sizes of 15. All right, and then I'll enter this, and it said round to 2 decimal places. Now it doesn't say round up or round down, just round, so the normal rounding. 9.7, so a mean value of 9.73 centimeters would have 30% below it and 70% above it, 9.73. So again, please read carefully like I did not. All right, and the first one, it doesn't say round up or round down, just round like you normally would. Wonderful. All right, so again, pay attention. I did everything right. Again, I did everything correctly in that first one. So if you followed what I did there, you'd be golden. You just had to round that one value up instead of down like I did. Okay. All right, so this is the other way around, this objective. This is, you know values now, and you want to find area under the curve. So you're going to be using normal CDF. So this is no different than something I did in section 7.1, but I will read through and I'll draw a picture for this first one and then probably just cheat the way through the rest of them. All right, so at a financial services company, the mean percent allocation for bonds in a retirement portfolio is 26.9%. So 26.9 is mu, with a standard deviation, population standard deviation of 3.6. So this 3.6 is sigma. So I've got mu, I've got sigma. A random sample of size 35. So this 35 is N, right? 35 retirement plan participants was taken. And the probability that the mean bond percent for the sample will be at least 28% was determined. All right. What is the probability? Well, first of all, was the probability a left tail, right tail, or interval probability? Left tail means to the left of some value, right means to the right of some value, interval means between two values. Well, at least 28 means 28 or more. So that's 28 and then to the right. So this is a right-tailed one, and again, I'll draw a picture. We can see that it'll be a right tail probability. And then use a calculator to find the probability that the mean bond percent for the sample of size 35, will be at least 28%. Right, so again, I'm going to go to a picture and draw a little picture here with a normal curve. All right, so this time our X bar represents the mean bond, the average bond percent in a retirement portfolio. I'm not going to write all that for a group of 35. All right, so again, n equals 35. Now, because this sample size is large enough, right, it's 30 or greater, doesn't matter what the original population's distribution was. By the central limit theorem, right, CLT, the distribution for this X bar, these means for groups of size 35, should be approximately normal, with a mean equal to the mean of the original population. So the mean of the original population, that was 26.9, and a standard deviation equal to the standard deviation of the population, 3.6, divided by the square root of the sample size, which we'll have the calculator just do for us. Right. And I'll draw a little picture. Right, here's possible mean, average bond percentages for groups of 35, right? Different values of X bar. It's normal here, and we're, underneath the peak should be 26.9. Then underneath these inflection points should be this distance. Whatever 3.6 divided by the square root of 35 is, that's the distance to these points under the inflection points here, the values under the inflection points. Now, we are given the value, they say, what is the, find the probability. Right, they want us to find the probability that this, this mean bond percent, this X bar, is greater than or equal to 28. Right. So let me draw a picture of that. Now 28 is going to be somewhere over here. I don't know if it's beyond the inflection point, so bear with me here. There's 28, and we want at least 28. All right, so 28 or greater. And we're talking this entire area to the right. So you can definitely see it's a right tail probability. Now I just want the area, and I'm going to do that by using the normal CDF. All right. So calculator's up already. I want to find an area under a normal curve. You go second, distributions, down to that normal CDF. Now, what's the lower value in this region? It is 28. What is the upper value? Well, there is none, right? It goes up forever, to the right forever. So what I'm going to do is, put in some very, very, very large positive numbers, something that would be many, many, many standard deviations away from the middle. So again, I like to just do 5 nines, right? Maybe even 6 nines, just some big positive number to indicate that there's no upper value really. What's the mean of this distribution? The distribution of the x bars here, that's 26.9. And the standard deviation, I'm just going to enter it the way it is here. It's the standard deviation of the original population, 3.6, divided by the square root of the sample size. Close parentheses. And then we get here. So the probability is approximately 0.0353. Right. So this is definitely too far. This is I put it too close to the mean. This is only about 3%, a little more than 3%. All right, so back here, right, we said it was a right tail probability, and our probability is 0.035. Right, but notice though they're trying to trick you. Right? They got 0.035 twice, but remember how the probability was written. It was at least 28. This mean bond percentage was at least 28. That's greater than or equal to 28, not less than 28. Okay. All right, and then we'll continue on. And again, I think I'm going to just cheat on the rest of these because they're all very similar. Okay, yeah, this is basically the same kind of problem. So I'll leave it to you. Do it the same way I did the first one, with a normal CDF in some fashion. You just have to know the mean of the x-bar distribution and the standard deviation of the x-bar distribution, and what's the left value and right value of the region you're trying to find the area of. Okay, so yeah, this is... Alright, this one's a little different, but pretty much the same. Because here you're given an original population mean of... Alright, so a psychologist believes a majority of people have dreams that last less than 7 minutes. Assume that the length of a dream follows an unknown distribution. So say x represents the length of a dream, and the mean of that population is 6 minutes, so that's mu, and standard deviation 2.4 minutes, that's sigma. The psychologist randomly selects 31 people, so this is n, and notice it's a size large enough to where the central limit theorem will apply. Right? It's 30 or greater, because the original population had an unknown distribution. Not you don't know if it's normal or not, but it doesn't matter. The sample size being taken is large enough to where the distribution of the means, right, x bar, the average dream length for a group of 31 people, should be approximately normal. Use a calculator to find the probability that the sample mean dream length is less than 7 minutes. Which I have down here, probably the x bar, right, the average dream length for these 31 people is less than 7 minutes. Now the mean of this distribution of the average dream lengths for 31 people should be the mean of the original population, which was 6 minutes. So round things to 3 decimal places. So the standard deviation for these averages, the average dream lengths for groups of 31 people, will be 2.4 divided by the square root of 31. And I'm gonna, they're asking me to round things to 3 decimal places. So let me pull the calculator up. So I got 2.4 divided by the square root of 31. And then to 3 decimal places, that'd be 0.431. Right, so 0.431. And then this probability, I'm going to do the normal CDF, right? Normal CDF. Now I'm going less than 7. So there's no lower value. That's a left tail probability. So I'm going to put in some big negative number, negative 99999. All right, something big and negative that's clearly way far left of the mean, many, many standard deviations below the mean. All right, then the upper value would be 7. All right, we're going up to 7, less than 7. The mean, we already said, was 6 minutes, and the standard deviation 2.4 divided by the square root of 31. All right, get that out there, and great. So the probability that, a group of 31 people has an average dream time less than 7 minutes is pretty high. 0.9898, almost 1, almost 90, this is almost close to 99%. In fact, that's what I'm going to enter because it says round to 3 decimal places. It's 0.9898. So I bumped this up to 0.990. All right, so the probability that a group of 31 people has an average dream length less than 7 minutes, 0.990, almost basically 99%. Very high probability. So that psychologist, I would say that psychologist, his belief is valid. Right? He believes a majority of people have dreams lasting less than 7 minutes, and there's a pretty high probability that a group of 31 people has that happen. So I'd say what that psychologist believes is pretty accurate. And we'll talk more about that, whether or not a belief is true or not, or whether a claim is true. That's going to be hypothesis testing. Going to be doing a lot more of that in later chapters. All right, and like I said, the rest of these pretty similar. All right, so this one is just like the last one. You got the mean, standard deviation, probability of some mean being less than 275. So again, I'm just going to cheat on this. You just have to figure out the right numbers that go where. All right. And then that last, and the only thing left to do is that inverse norm that I was showing you earlier. Right, where you're given area and have to find a value, right, using the inverse norm. So again, you just have to pay attention. You have to know what the mean of the x-bar distribution is, and what the standard deviation of the sample mean distribution, the x-bar distribution, is, and use the inverse norm. So again, I'm going to cheat on this and be done with it. All right, and I believe that is all. Wow, it's because I got one wrong. They're going to have me do more of these. So yeah, just read carefully again, like I didn't in that one problem. It says round these values to 2 decimal places. Okay. And it doesn't say round up or round down, just do the normal rounding. So again, same kind of problem. Just going to cheat here. Doing the same stuff I showed you earlier. All right. There. Okay. So you have the normal approximation to the binomial, where the central limit theorem doesn't really show up, but it applies in the fact that the larger the sample size is, the larger the value of n is, the more number of trials you have, the closer to normal our histogram will look. And use areas under the normal curve to approximate, those bars, the areas of those bars in the binomial histogram. Remember, you're going to be using a lot of halves there. 7.5 to 8.5 will represent 8 successes, for example. And then you had, that central limit theorem for means coming back, using normal CDF to find area under curves, using inverse norm to find values on the number line. All right, so hopefully this video is a decent guide for you when you go through and do 7.3's assignment on your own. And hopefully you can learn from my mistakes as well, right? When I didn't read that one problem carefully enough, I said to round up. So just read carefully, pay attention to how they want answers entered. And if you have any questions, of course, come across any issues, let me know. And thank you very much for watching.